Okay, so we have this problem here that says a disk of mass m and radius r rotates at an angular velocity omega naught. Another disk of the same mass m and radius r, different r's, is dropped on top of the rotating disk such that their centers coincide. Now both disks now spin at a new angular velocity omega. What is omega? So to do this, we need to take advantage of the fact that your initial angular momentum will be equal to your final angular momentum. So we'll break this down. Your angular momentum initially is just from the one disk. So your angular momentum will be equal to I times omega. So the moment of inertia for a disk is 1/2 mr squared. That's for a disk. It's probably one that you'll be given. So L initial is equal to just 1/2 big M big R squared times omega naught for omega initial. So this is the angular momentum prior. Now the angular momentum final we also want to look at. And it's still going to be I omega. But what's the final moment of inertia? Well, you're still going to have that first disk. That's not going to change. But what we need to do is we need to add the new disk onto it. So that'll be a 1/2 big M little r squared. So then L equals 1/2 big M big R squared plus 1/2 big M little r squared omega final. And again, we know by conservation of angular momentum final should be the same as angular momentum initial. In other words, 1/2 big M big R squared omega naught equals 1/2 big M big R squared plus 1/2 big M little r squared omega. Just to simplify this a little bit, we can see that these 1/2s will go away and the mass will go another way. So R squared omega naught is equal to big R squared plus little r squared omega. And then all we have to do is divide over to get your final angular velocity is R squared over omega naught divided by big R squared plus little r squared. So super easy problem actually. But worth noting if you haven't seen this before, if you just want to review, what is it, R squared omega naught over, so option B. It's still good to just, I guess, be reminded of your equations for angular momentum, the idea that angular momentum is conserved. What do you do if you throw a disk on top of another disk? How do you approach that? But if you can do that, then you're just setting up the equation, doing a little bit of algebra, and there you go. So not too bad of a problem, but no reason to skip it, really.